Welcome to BayPIGgies. You know, I went on an audition for a commercial a few weeks back, and they said, "Don't call us, we'll call you." And they never called. But apparently, Python's more reliable than that. So I'm here to introduce Alex Martelli's talk. Alex Martelli is a rock star. A few years ago, he was an Italian rock star. He's the author of Python in a Nutshell, and is the curator of the Python cookbook. And if you ever get in an argument, a language lawyering argument, you don't want this guy on the other side of it. So, Alex Martelli.
Thank you. Welcome, everybody, to this monthly meeting of BayPIGgies. So, just in case you've got to run, that's the one thing that matters in the talk, because it's where you can download. It's where you can download the PDF, which has all my slides. So the audience for this talk is meant to be pretty broad. I'm trying to talk to almost everybody. If you don't know any Python, if you're at the very beginning of the journey, it will probably be above your head. If you know a bit more Python than I do, like my friend Valentino right here, you'll probably get bored, but he's a friend, so he'll be patient about that. But for most of us, the talk should, I hope, be appropriate and interesting. So let's get started. What's the general concept of a callback? Why back? What does it refer to? Well, once upon a time, the concept was of writing libraries, which was invented in the 50s within the Fortran community and then others, was, well, I make a lot of useful functions and procedures, put them together in a library, and your application code calls into them, so I can do some computation for you and give you the result. So that was the normal way of doing things. It still pretty much is. If you look at the documentation of some application programming interface, an API, it's mostly going to consist of what do you call to make certain things happen or to get some computations done on your behalf or data stored or sent somewhere. But once in a while, there is a use for something that's exactly flipped backwards. Instead of you calling, well, in addition to you calling entry points in the library or framework, you arrange things so that the framework calls entry point in your application code. Indeed, the very term framework, as opposed to the more traditional one, library, was introduced in the late 70s, early 80s to try and describe this kind of arrangement, where basically, instead of giving you a series of bricks to build your house with, you are being given the blueprint and just requested to supply some bricks to fill in the outline. This has been called for over 20 years now. I looked up the exact date of the reference, got kind of scared. Oh my God, it was more than 20 years ago. I remember when I read this first, in the original publication, and I wasn't exactly a spring chicken even then. It's been called the Hollywood Principle, exactly because of what JJ was explaining. That is, you'd go and try out for something, and, well, thank you very much. Just don't call us, we'll call you. Meaning or implying that, well, actually, probably they won't bother to if they find anybody who's more appropriate or more suitable for the role. But in Mesa was not necessarily the first language introducing the concept, but it was the one in which the nickname Hollywood Principle was coined. The call actually happens reliably. And it's still funny to call it the Hollywood Principle anyway. So why would we do that? I mean, it's pretty easy to see why we would want to call into the library, because the library may have funky algorithms and very optimized stuff to do work on our behalf. But why would we want the library to call back to our application code? What's what is it we gain that way? There's essentially two groups of users which we'll see. One is customization. The traditional approach to customize details of the behavior of some piece of code is basically by giving that piece of code certain parameters, configuration values, configuration settings, flags, call them as you will. The problem is that those get passed once and need to stay essentially fixed throughout the execution in which you've passed them. The callback principle basically lets the piece of code you're customizing call back into your code to get the parameter it must use, and that parameter may change from moment to moment depending on your exact need. So there's no more flexible way of arranging a customization architecture than by callbacks. The other large area is what I call event-driven architectures. And I'll split that later in the talk between actual events, which is where actually something happens, there's an event, and pseudo-events, which are just a way to structure elegantly and flexibly the control flow of a whole program. But let's not get too far ahead of our thread. So how is a callback implemented? It's pretty easy to recognize it. You've seen a lot. We'll point out some cases. But anytime you hand a callable over to somebody, some function or method, the somebody may, as needed, store that callback or a reference to that callback somewhere into a container or maybe just as a local variable as long as it persists long enough. And when appropriate, which is, of course, what distinguishes various callback situations, it calls that callable. For example, it does it when the framework calls the callable you'd originally passed to it when it needs some specific functionality. That is the customization case. Alternatively, it calls it when appropriate events have occurred. And what's an appropriate event? Depending on the use cases, and we'll get into a lot of details, it could mean a change of state, some state has changed, or the user, a human being. Unfortunately, we still have those. We have not perfected the system yet. The computers mostly talk to each other, but once in a while they still have to do to those slow and reliable external systems. So that they end up, I don't know, clicking the mouse. Why are they clicking the mouse? I don't know, but we have to do something about it. Or more normally, when you're interacting with other computers or other pieces of hardware, network events, other I/O, like the disk has finished spinning, timeout, as in we've been waiting for too long in this thing which was supposed to happen, hasn't happened, system event, the CPU is on fire, and other useful alerts. Or when no actual event occur, we made something up, because otherwise it would be too boring. We'd never use our powerful callbacks. So we make up some events and structure control flow. We'll get to that. Let's first examine customization, which is something that doesn't happen often today in the sartorial world, but happens a lot in the software. So not in the fine ware, but in the software. Let's take one of the simplest examples that you're probably using every day whenever you're programming Python. When you are sorting some sequence, almost always you want to sort it in a specific way. Occasionally, it happens that the natural sort, lexicographical sort with small numbers and early alphabetical letters are first and bigger ones are later, suits your purposes. More often than not, you want to do something slightly different. And the best way to tell sort exactly what you want to do in terms of sorting is to pass a key parameter to the sort method or the sorted built-in function, if that's what you're using. Before Raymond Hettinger introduced this little callback trick, this is how we used to perform this task. Unfortunately, many people did it the wrong way by passing the CMP parameter, which was a design error, mutated from C into Python and has stuck around far too long. Don't use it. It's a bad design because basically it ends up being called n log n times. That is a lot of times. In this approach, your function gets called only n times, which makes a substantial difference. So when we had to call what I nicknamed decorate, sort, and decorate, or DSU pattern, basically we take a list as input and a callable key, and we prepare an auxiliary list of tuples. Each of them has the index and the value, which I get enumerating the list, but preceded by the result obtained by applying the key callable to the value. And then I sort not the original list, but rather this auxiliary list of tuples. And finally, I extract the values only and set them as the new content of the list object. When you call mylist.sort key equals something, this is basically what it's going to do inside, although it's going to do it much faster and smoother than it would be possible in Python because it's all built in as part of the internals of sort. So basically, it tags every value with this key only. And it also guarantees that two values which correspond to the same result for key remain stable. So they don't get swapped. Here I had to basically add the index as part of what I was sorting to make sure that there was not a swap. So we want to sort a list of strings in a case-insensitive way. A simple way is uppercase every string in terms of sorting order. So I'm calling str to upper, the to upper method of the string type, and that gets applied to each and every string. This is kind of a weird way to do things if you think in object-oriented terms, because in object-oriented terms, you normally want to call a certain method on each item, not on a type, passing it the item. Unfortunately, there's no way to express that in a Python callable except the incredibly clumsy lambda, which I never recommend. So essentially, this is a start of an indication that callback, although it was introduced in Mesa, which to some extent was an object-oriented language, is more of a functional idiom than an object-oriented idiom. Now, Python does both functional and object-oriented, but there's a certain impedance mismatch between the two, and this is one of the cases in which it shows through just a little bit. What would be the object-oriented approach to customizing if callbacks fit only up to a point in a thoroughly object-oriented view of the world? The answer is what I have presented at length. These URLs give you the video and a PDF as probably the single most significant design pattern, the template method design pattern. In the template method design pattern, you put the framework functionality in a class that is intended to act as parent, and that has a method called the template method, or the organizing method, which in turn calls hook methods on the self object. And the customization is by inheritance and overriding. It's perfectly object-oriented, it's handy, it's compact, it's incredibly rigid. Sometimes it's what you want, but as you'll see if you follow this presentation, it takes all the dynamism of Python and then some to make it really usable in the real world in most cases. Callbacks, on the other hand, are inherently maximally flexible. So that's the trade-off. If you want to be an OO purist, go ahead and use template method. If you want to get things done in the real world, consider all the advanced versions of template method that I present here, or go with callbacks and live happily ever after. Another example is the concept of scheduling. Scheduling means being able to register things that must be done at certain times and making sure they get done in the proper order. The Python standard library offers a module for that. It's called sched. And probably the most natural way to design it would be to hard code the measurement of time by calling time.time to find out what time it is, time.sleep to do nothing until for a certain period of time you have nothing scheduled for, and so on. However, the designers of the sched module considered and easily found a way to achieve much higher flexibility in the exact functionality of their module. Instead of knowing, by basically reaching into the time module, how you tell what time it is and how you just sleep for a certain number of seconds, you instantiate scheduler objects by passing them callbacks for that purpose. The way sched is actually designed is the functional programming way, the more flexible one, where you pass two separate callbacks, one to tell what time it is and one to just let time pass. The object-oriented way in this case would be to pass the object which has those methods. But this is more flexible, and the designers of sched went for flexibility. Why is it important to be able to pass a fake way to measure time? Well, because this increases the uses of sched enormously, also makes it much easier to test decently. If you are unit testing a piece of code that at some point does a time sleep 99, you don't really want to wait 99 seconds every time you run a test, what they use. You need to fake out the time sleep. One approach is the so-called monkey patching, very popular in the Ruby world, which is basically reach into the time module and set a fake sleep function there. That kind of works almost, except for the global repercussions of it. Or else there is the elegant way known as the dependency injection design pattern, which is basically let the thing that needs to sleep take the sleep callback as an argument, which is what we do here. And also, there's many cases in which your concept of time is actually just something that goes linearly, but it could be demarcated by network events, for example. There's never the need to have anything happen unless something is happening on the networks. With sched, you're basically just using a infinite sleep, in this case, for time sleep, which does absolutely nothing until something happens on the network, and for the measurement of time, just anything that gets woken up by a network event, and so on and so forth. There's enormous flexibility in how you customize sleep. So this is the whole part of the talk regarding the use of callbacks for customization purposes. Are there questions on this part specifically?
You were talking about list.sort and passing a function for the keyword parameter, and you were saying that it was non-object oriented, and that's a painful thing. Can't you pass an unbound method, and won't that work out okay?
Can you pass what?
An unbound method, so class.
That's what I'm doing. STR.
Oh, okay.
And so if I have a mix of objects which are, for example, plain and Unicode strings, it breaks. Because it needs, I have just constrained the thing. If I have a subclass of string that overrides the uppercase, the override doesn't take, because I'm using. There's also, I wouldn't call it object-oriented if it doesn't support inheritance. Anything else? No? Shall we move on? Anybody recognize why I choose this to represent events? I'm actually an engineer, but that's pretty close as a definition. Thank you very much. Okay. What's an event? There's basically two classes, or categories or kinds. There's proper events, things that actually happen in the real world, and there's pseudo events that I'm essentially using for the purpose of structuring the execution of my program. So what's a proper event? Well, GUI frameworks are plenty of those because things happen. People move the mouse, click on buttons, click on the keyboard, spill coffee on the keyboard, or the cats walk across it. Each of this is probably a number of events, particularly the cat, and that need to be dealt with, possibly by yelling at the cat and chasing him out of the room. But that's up to the application. Then there's the observer, or more completely, observer-observable design pattern, which is basically all about state changes, as we'll see. Then there's asynchronous, or also known as event-driven I/O, mostly network, but it works for a lot of kinds of I/O. And then there are what I deem system events, which are, well, we'll see them in detail in the course of the presentation. And then there's pseudo events. So once you start doing event-driven programming, typically because you're dealing with real events, you originally may have a little bit of difficulty wrapping your mind around to it. Instead of you calling things and making things happen, things just happen to you and you get called to deal with it. It seems the world in reverse. But after a while, you know the Stockholm syndrome? Have you ever heard about this? You get used to it and you crave more. And so instead of just limiting yourself to the events that actually happen in the real world, you start simulating events just so you can respond to them. The best example, actually, joking apart, is event-driven parsing. The first time I heard this sentence, I thought it was a Markov model generator of text to run amok. I know parsing. There's like recursive top-down descent and bottom-up. I know Yak. I know what's event-driven about parsing? And then I found out, and it actually works. Then there's scheduled callback. We've already mentioned sched in terms of customization, but in the end, the whole purpose of sched is basically making events up on your request to call you back, as we'll see. And then there's concurrency, threads and the like. And finally, there's timing, debugging, and the like, which we'll see at the very end. So what about the GUI frameworks? Well, those are the most classic. Basically, the whole invention of event-driven programming, or at the very least, they're spread like wildfire starting maybe 30 years ago or a bit later, was due to the emergency of graphical user interfaces. Because, programming a graphical user interface in any other way, and people have tried, absolutely the wrong way. Sucks hard rocks. You never want to. I don't know if you can probably still find some old and rusty GUI framework that tries to not work in an event-driven way, but don't even try using it. TK Inter has two classes of callbacks. One is for the most elementary kind, which are events basically boiled down to their very essence. A button gets clicked, a button meaning not a mouse button, but a simulated button in the GUI painted on screen. Well, in this case, it's a simple click, and there's one thing happen, no parameters to it, no nothing, you get a callback. And that's the command equal parameter in button. And similarly for other, something has been chosen in a combo box, that kind of thing. Very simple from the programmatic point of view, representing a series of action by the user and response by the graphical user interface. And then there's a bind call, which is a complete other ball of wax. It's basically the binding of a handler to a class of events, either on a window or on a widget or on a class of widgets. It's actually, I think TK Inter goes a bit overboard in that. You can do a lot of things with much simpler ways. But basically here the event is taken as a string in a language which actually describes the event. So for example, it could be quote less than key greater than, this means any key on the keyboard, or it could be quote A quote, which means just the A key on the keyboard. Or it could be enter or leave, the mouse pointer entering or exiting a certain rectangular area, and so on and so forth. It's a tiny and very simple language that gets interpreted when you bind something. And then the handler is where the callback happens, and it's a callable that takes the event argument as the only parameter. And then the event argument has a lot of attributes with X and Y for the mouse, type of events, widget, what widget it happened on, and you can also buy by class, you can buy by root window. The event and what object you call the bind on are basically even too flexible. But basically, you can deal with any user behavior and happenings as events in this way. Another classic, which has possibly been the first way to, after the model view controller framework, the observer observable has been a generalization that still lets you build MVC on top of it, but is more general. Because basically, an observer is a target object. Sorry, an observable is a target object that lets you add observers, which in the general case could be callables, although often, because it's expressed in an object-oriented way, they rather need to be objects. But the point is that whenever the target state changes, the target knows and reacts to the change by treating it as an event, which is a reasonable thing, and calling back to all the observers. So this means that there is no one-to-one tie, because any number of observers can be, at a given time, observing any given observable. So you could have, for example, a temperature sensor, which, when the temperature changes, tells an observer which is going to draw a pretty graph, and another observer which is going to spray anti-fire fluid if the temperature has gone above 400 degrees. And the two things are not mutually exclusive. I hope the sprayer has precedence, but that's or at least happens pretty soon. So there's a lot of design choices in an observer DP implementation. I think if you read the treatment of it in the classic Gang of Four design patterns book, it's really very good, as is all of the book. But essentially, your choices, you can have general observers, specific observers, or grouped observers. A general observer is essentially an observer that is asking, call me on any state change. It works, but typically you don't really want to do something in front of any state change, but only some of them. The state changes of, for example, a temperature sensor could be any temperature change. Most of them will be totally irrelevant for the fire prevention system. Or you could have an event which is when the temperature goes above 400. That is very relevant to the fire prevention system. So the general observer has a lot of work to do, typically, to select, after having been alerted, okay, am I really interested in this alert or not? A specific observer is a callback on specific state changes, may be a bit harder to design, because basically you need to be able, when you set the observer, to specify with reasonable precision exactly what events are of interest. How specific are you being? Which may vary. And then we have grouped observers, which may in some cases be an excellent compromise. These are typically objects with several methods. Different methods can be called for different events, for different kinds of state changes. And in Python in particular, given good introspection, it's pretty easy to make that selective. So you could have a class of temperature sensor observers which implement method any change and fire risk change. In the any change method, if implemented, gets called every time the temperature changes, and the fire risk one gets only called above 400 Fahrenheit. Of course, this is kind of rigid in that you need to do it at design time, except in Python you can actually bend that rigidity a bit because the introspection and dynamicity together can be very powerful. But it's, again, kind of, you need to define a language in a very restricted sense of the word language of events that may be of interest to some observers and not others. With general observers, you don't have that problem. At design time, you have to basically code at runtime, I mean, execute at runtime the code, but it is more flexible. What are you going to tell the callback? I mean, what arguments are going to be used at call time? The first and simplest choice is arguments. What arguments? We're quiet people. We don't like to argue. No arguments. And that's what tkinter does with the command equals callable of buttons. That's what argument you want. It's been clicked. What argument can there be? No, it hasn't. Yes, it has. No, it hasn't. That's not an argument. That's contradiction, in honor of Monty Python, for which our beloved language is named. That only really works at all in the very simplest cases. In Observer, the natural choice is to pass as argument the target object whose state just changed. This way, you can have a sensor, an observer observe many observables. Say the fire alarm could be observing 20 temperature sensors. When one temperature sensor goes above 400, it alerts, it calls back into the observer, and passes itself as an object to as one argument in the call. So, but basically, the fire alarm system knows where to direct the flow of high-pressure water, or for what warehouse to call the fire department, and so on. So that it is a natural choice. It gives plenty of flexibility. It basically may require the observer to engage in a dialogue to find out exactly how did the state change, because basically the only information it gets at call time is the state has changed, and it was my state. Okay, was it the temperature? No. Was it the pressure? No. Does it sound like pressure? It can be kind of plus there's round trips. So in some cases, it makes much more sense to define what kind of, to summarize the state changes. For example, if an observer has many many attributes that constitute his state, it could be useful to send a dictionary of attribute old value, new value. Sometimes that is all that's needed. On the other hand, you save the round trips, which may be very relevant if you're talking about network communication, because a round trip can take milliseconds. But you are sending a bigger bunch of stuff, which may not be of interest at all. So, as usual, there's trade-offs. The point of this talk is being aware of the trade-offs, so that when you do your design, you can make the trade-offs appropriately, and when you're using somebody else's design, you can whine about how they misdesigned things.
Right. And it seems like there's one other, I think, possible case, which is, what if you had a callback for every state change? So, for example, you had one for temperature, one for pressure, one for...
That's the other...
So
that's the other thing, the grouped observer.
Right, but what you do this is because that method immediately doesn't require any additional parsing. It doesn't require any additional grouping. It doesn't.
Well, it still requires to know, okay, the temperature changed from where to where. And when did you last measure it? So the fact that you know that out of the many characteristics what changed is the temperature still may require, to understand the proper response, one or more interactions with the object. What was your previous temperature? What is your current temperature? At what time did you take the latest temperature measurement? What time had you taken the previous one? It's not necessarily all that you need to know. And yes, the grouped observers do basically parse it that way and also make things a bit easier because, particularly in Python, it's pretty easy to just not, if you don't care about pressure, you just don't implement the pressure changed method and don't get a callback at all, which saves time. On the other hand, for these cases, you do need to know in advance exactly what parameters can possibly be observed. Or again, you can use Python's introspection and dynamicity to kind of obviate it. But sending a dictionary is a pretty general way, except that the dictionary can grow a bit large, as I said, particularly if you are measuring maybe rate of change as well as value. So I'm focusing for this very hypothetical example on physical objects like a temperature sensor and so on, but I hope you realize this applies to even completely abstract objects in exactly the same way, just maybe easier to visualize the sensor. Okay. Another typically useful, if not a description of the state changes, they may not be necessarily continuous values, so that such things as rate of change and so on may not make any sense. But there may still be possible to basically construct an identifier, a description of the event, which may be sufficient to the observer saving a round trip. The event may or may not be conceptualized as a state change. In terms of observer observable, I always start thinking in terms of state change, but it can actually apply to other events. They can always be kind of put false mustache on and say, hello, I'm a change of state, whether it is or not. But there's another group of arguments which are very easy to forget. Some arguments are related to the target or the event, but others may be related to the callable. Now, you could always say, for example, take the trivial example of the command equals something, which doesn't take any argument. Well, what if I actually want to attach basically the same response to 10 different buttons, except I need to know which button it is, and the thing is not passing me? Well, basically, I need to attach different pre-decided arguments. That was basically the kind of problem we were discussing. You basically want to pass the same thing, but with different pre-decided arguments, which don't really depend on the event. They depend on the callable. At least this is how we're conceptualizing that. And this is the Python architected way to do it. Given any callable, you can predetermine some of its argument, positional and keyword, by calling functools partial on it. Functools partial returns another callable where some arguments are already solved, and you can't pass them again. And this is extremely general and very useful. I used to know it as currying in functional programming, but I'm told that currying isn't really the appropriate verbiage. Nothing to do with Indian cuisine. However, notice how different it is to call a set callback if you could pass the function and the pre-bound arguments versus if you have to wrap those in functools partial. Yes, the first one is more general, but how much more elegant and smooth is the second idea? Or almost as if you just passed A and KW without the stars, just the tuple of arguments and the dictionary of keywords. It's far neater. Some callback systems in Python have noticed this and support this, but not all, unfortunately. So what I'm telling you is when you're designing a callback system, please do support this approach because it's so much neater. When you're using one you're not familiar with, check if by any chance the designers were good designers and are supporting it, so you don't need to use functional partials. Now we come to the interesting problem of dispatching. For example, it is typical for observable, and in some other callback cases, we may have set more than one callback. We may want to set more than one callback. What do we do if multiple callbacks get set? If you're familiar with, I don't know, hardware interrupts, for example, the typical situation is the CPU has a little table with like 256 addresses, one per level of interrupt from 0 to 255. When you set an interrupt handler there, well, whatever was set there isn't there anymore, and so only the latest one will be remembered. And some people, particularly in the early days of callback system design, well, they work this way. When interrupt 24 happens, I want this to be handling it. Or when the event happens, I want this callback, singular. It's simple. It's particularly simple to implement because basically you only need to have your who am I going to call back attribute. No. But it's very rough. It's, as soon as you want to become a little bit more general, you have to start making some decisions. If you remember all the callbacks that haven't been set for that event, and the idea is you want to call them all, well, in what order are you going to call them? Last in, first out? First in, first out? Oh, and by the way, don't forget you will have to have a specific method to remove a callback from the list. Because if there was only one callback, it's pretty obvious that if you set it to none or 0 or something like that, it means forget it, I don't want this callback anymore. But if you can set any number, well, then you had better be able to remove some as well as add some to this list. And if you do have a specified order, do you let one callback along the chain decide, I have really completely handled this event. I don't want any of those coming downstream for me to even get disturbed. So basically blocking the thing and preempting others. Vice versa, in single callback systems, a typical idiom is to set a new callback, you get and save somewhere the previous one, and the last thing the new callback does when it's finished is chain to the previous callback, which is clunky, but anybody who's programmed for Microsoft DOS in the 80s know what I'm talking about. That was the typical approach then. Also, it's the only way you can really do multiple interrupt handling if you're programming on the bare metal, essentially. Also, can you somehow group the events or the state changes? This is a different way of seeing the grouped callbacks. The point being, instead of a single callable, can I use an object with many methods that will receive calls? And how does that interact with dispatching? This is a pretty difficult design decision. Another sense in which you could group it, I would use the word batch. If actually performing the callback function is costly, you may want to not do the callback instantly. That only basically applies to network situation. Something that happens in certain cases is that the data is arriving, I want to give it immediately, except that each act of giving is heavy because, for example, I have to take maybe these 2 bytes and wrap them in 45 bytes of headers and packet. Well, can I wait 2 milliseconds because more data is likely to arrive all bunched together? So instead of doing 10 times 2 bytes plus 45 each time, I send the 20 bytes only once. But that's more of an optimization for real-time performance. And to be perfectly honest, you're unlikely to be realizing that in Python, although it's not impossible.
That actually sometimes happens in GUI situations too, where you're having a painting or something that you're manipulating with DSP algorithms to find things that you actually a guy may click the button a number of times, and you can't do the whole thing. You do part of it to make it look like it's happening, but you don't do the full thing.
Yeah, very good point. You don't really want it to happen in stuttering fashion. You want a smooth transformation to happen. Plus, if you're designing a dispatch system, you need also to decide whether an error or anomaly or exception is an event just like any other or is really deserving of different treatment. Which is kind of like the choice in Unix of using standard output for normal results versus standard error for anomalous results, so that anybody who's like in a pipeline just computing normal result doesn't have to start worrying what if it was an error instead. So for the best solution, or at least one very well thought out solution to all of this problem, I strongly suggest this paper. This paper, from many years ago actually, introduced a data type known as the deferred type as part of the twisted matrix system, but you don't have to be into asynchronous network programming, although everybody should be, as Valentino, who's one of the core developers of this, no doubt would argue. But it can be used on its own just to structure your callback. The idea is basically you have two chains. One is a chain of callbacks for success cases. One is a chain of callback, let's call them, for error cases. And you can go from one to the other if an exception gets raised or gets handled. And it works like a Unix pipeline in that basically forgetting the errors, the result of every callback is the argument of the next one, and you also get the ability to pre-bind arguments. So it's really very well designed. Now, another popular class of events are system events. For example, one system event is death, meaning program termination, or exit. It's pretty common to want a callback when the program is exiting, because you need to do some cleanup. For example, there are, in some cases, and depending on the system, you may not want to delete all the temporary files you may be leaving around until you know you're done with them, and you only know for sure you're done with them when the whole program is exiting. Where do you put the cleanup? Where do you put the removal of all these temporary files that aren't needed anymore? You put them in a callable and register it with the @exit module of the standard library. All the callables that you've recorded with @exit register are going to be called, I think last in, first out, but I don't really remember, but just before the program is about to terminate. No other application code is going to be called. Signal is a quirky, historically based on Unix way to get almost asynchronous calls smack into your handlers. And this is a typical example of very old design for callbacks. For each signal number, you have one handler. Not 0, not 2, 1. What happens is that when you install a callable for a certain signal number, you get the callable that was previously installed as the result, so you can do chaining, like you could in DOS. Indeed, this is a 1970 design, and it shows. It's basically from the very earliest Unix. Other examples. Unfortunately, there's some. So display hook and accept hook are things that you can set. So you say sys.displayHook equals my display function. And this means that every time the interactive interpreter wants to display something, instead of just doing repr on that thing and putting it on screen, it will call my display function with that thing. Accept hook similarly is how the interactive interpreter, what the interactive interpreter displays exceptions, typically a trace back and so on, but you can do whatever you want. But if you want to set a trace function or a profile function, that you do in a more Java-y way. Instead of just saying sys.trace equal blah, you have to do sys.setTrace of blah. There's no real reason. It's all historical junk. as is the complexity of the set trace callable. But the point is that, so for example, set trace events are, I'm about to execute a line of Python code. So for the system, the Python system, it's a relevant event. It's important that you are able to actually do something in this case. Or I'm about to call the following function. Or the function has returned with the result of so-and-so. Set profile is called in a similar set of situations. It's not called for the single line, but it's also called for C-coded functions. And an extension module can define its own system events. For example, readline has, among many other events, a startup event that is basically, I'm starting up readline, about to accept input for the first time. This is, I'm about to accept input once more, pre-input hook. This is the user has hit a tab and is asking for completion of the string. So they're all events, in this case, in part, their user interface, although not graphical. They're still user interface events. But I'm treating them as a part of system events because they're basically handled in very much the same way. It's not an entirely event-driven system. It's just that once in a while, in the middle of doing something, so you call row input. Give me a line that the user types, and you have read-long installed, well, that will cause a callback to your pre-input hook, maybe to the completer, maybe to other callbacks that the read-line module does. Eventually, your main line of code gets, again, controlled because row input returns, and there's a string ready for you. And finally, if you really get addicted to event, you will find yourself using pseudo events. Events we make up because they're such a nice way to structure our execution. Parsing is possibly the best example. Scheduling, we've seen half of it, we'll see the completion, and then there's concurrency, there's timing, there's debugging, and many others we want. So event-driven parsing, the best example is SACS. So lots of people can stand it and really want to use DOM or something lighter weight, better designed than DOM, like element tree. But the concept of SACS is that, at least for XML, parsing can be seen as a sequence of events if you squint the right way. The events are basically, a tag is opened, and this is the tag name, these are the attributes. There is text content, here it comes, and a tag is closed. And this is the tag that was closed. And that's all there is to it. There's nothing else. You read from the beginning to the end. Well, there's processing instructions and comments and junk. But why is this good? Because the XML document is sometimes huge and is sometimes coming at you gradually from a disk, a few megabytes at a time. And I'm not joking when I say it can be really huge, so a few megabytes at a time. You don't have to wait until you've seen it all to do event-driven parsing. You can start generating event to the application code as soon as you've seen the tags and the piece of text, another piece of text, and the closing tag. And meanwhile, the document keeps coming. It may even be coming through a pipeline or a network, in which case it could be even slower. Event-driven parsing means you don't have to have it all. And it means even if you're handling a 50 gigabyte file, you don't need 500 gigabyte of RAM to build a complete model. You just do it a little at a time, because from the point of view of the application, it probably will not care at all about most tags, or at least that's a pretty typical application when you're parsing XML. So the XML is a, say, a library, which is a sequence of books, and books have a tag which says the title and the author, and the content, which is the whole book, for example, which is a bit big. So you only want to know the title of books by Isaac Asimov. But the only way you can do it is from this 50 gigabyte stream. Doing it with the DOM would be suicide. Doing it with SACS is reasonable. You basically notice, okay, a book is starting, and start keeping note. And this is the title, and the author is Robert Heinlein. I don't care, poof. I just wait until I get the closed book. And then, oh, Isaac Asimov, okay, let's record the title in a tiny structure on the side, and then ignore the rest until the book is closed. So the parsing by event is actually as performant as XML itself lets it be, because you cannot say, okay, fine, I don't care, skip ahead. You have to sit through the whole thing. It's like one of my talks. You can't fast forward if you're present here in person. But still, you don't have to listen until an event happens. Maybe I move on to a more interesting slide or something. And so event-driven following of TechTalks is kind of like event-driven parsing. Yeah, the other extreme, of course, is the DOM. There's also an intermediate system invented by our own Paul Presco, which is a pull DOM, which makes me wish I'd had another hour, which I don't. I'm almost finished. Because instead of doing callbacks, it does streaming, which is the duality which is so hardly ever recognized. Instead of calling you for the tags, it gives you a stream of the tags. And the reason it's called the pull DOM is that when you find a tag you're really interested in, you can tell pull DOM, oh, fill out that little branch of the DOM tree, so that you can then play in it at your out content is probably going to be very localized. The callbacks and streams and iterators in Python terms are kind of dual. There's a lot of situations in which you can use both. If you think of Ruby iterators, they're based on callbacks. Python iterators are based on streaming. Python iterator gets the items out at your code, while in Ruby, your code gets called back for each item. So I have more sympathy for the streams, of course, but even though this talk is about callbacks. So that's what we're talking about. Another example of manufactured event is schedule. We all have schedules, and we all know they're pretty much made up. I mean, there's nothing. The meeting starts at 9 sharp. Why? What happens after that? A meteor strikes? No, nothing. But it's still, we have this event at 9. That's a manufactured event. Well, we better do that if we want to be basically all in the same place at the same time. And that's what sched is for, actually. So you call it with the time and delay function, and then you can enter in the schedule, after this much time with this priority, please call this callable with this argument. Or at this absolute time with this priority, basically the same thing, except count time from 0 instead of from right now. You get an event token as a return, which you can cancel at some point. It's like, oh, I can't make it to the meeting, that kind of thing. When you are done preparing the first version of your schedule, you call srun, which just keeps running events with the recommended timing and so on. So basically, solve one callback after the other at specified times. And if you ever get an exception from one of the callables, that basically ends up propagating, but you can catch it outside of run, and then it is guaranteed by the semantics of sched, the queue of events after that will not have been disturbed. So you can basically catch exceptions from outside the scheduler and continue the schedule from then on. It's a really, really well-designed module. I use it a lot. I much prefer it to cron, by the way. If I can ever keep my own daemon running, I don't want to depend on cron's weird issues. Then there's concurrency. Threading is the most popular form, although we could talk longly and bitterly about it, but it's still very popular. And the basic, okay, you can do it the object-oriented way by subclassing thread and be a nice Java-like programmer, or you can do it the practical way and pass a callable to the target keyword, and this is the Python way, really. And then it calls target. And the key point, of course, is it calls it in a separate thread. That's the whole point, and it's really only useful if you're going to do blocking I/O a lot. And yes, twisted is a better way to arrange things, even in this case. I entirely agree with you. However, in some cases where you want very cooperative threading and you want really want to have hundreds of thousands of thread around, then even twisted would, on a single CPU, or even multi-core, be kind of. But you can use the stackless Python approach, where you basically have stacklets. And a stacklet has tasklets. It's all very, very cutesy. And a tasklet is a callable. And depending on the setup, everything gets called back. If it's active in front of queue, it's pure round robin, very, very simple. And it's basically up to the tasklet to suspend itself to avoid taking up too much. It can use channels to communicate with other tasklets, reschedule them. It's a very elaborate pseudo-concurrent. I believe there is some real concurrency if you have a multi-core now, but I haven't actually looked into that. But it's very cool. On the other hand, if you just have something written with threading, but is not heavyweight enough for you, stackless is the other way around. It's incredibly lightweight, wonderfully fast. But sometimes you really want to use all of your 16 cores or 32 cores or however many, and then you should use, it used to be a third-party module called processing. There's now a standard library version called multiprocessing, starting with 2.6, which I believe has just been released in beta. So I suggest you try it out. And it basically does with processes what threading does with threads. And then there's network spaces, which is a completely different approach. They used to be called Linda spaces a long time ago. It's still alive, and it's got a great implementation for Python and a decent one for R, which is a very quirky statistical language. If you ever need to do distributed programming with Python and R, which is a pretty narrow niche, but if that's what you need, you should really look into that. And timing and debugging is, so for example, if you look at the timeit module, it doesn't take a callable, it takes a string. But that string is something it compiles and executes. So it's a callback in an indirect and kind of dynamic languagey way. But, we are a dynamic language. No, never mind. So the event is kind of very made up. The event for the setup string is once at the beginning. That's actually pretty typical even in real event system to have we're just starting event. But the event for statement is one more case in which I'm trying to measure your performance. So it's pretty, the point of timeit is find out exactly how many microsecond or fraction of microsecond it takes to do a particularly tiny idiom so you can pick the right one. So this is timing, precious timeit module. The PDB debugger also works by either string or callable because you have PDB run and you have run eval, which do exec and eval respectively, and you have PDB run call, which takes a callable and arguments. But they're both called back, except essentially that PDB run does a compile in addition, so you pass it a string, but there's no real constraint. Okay, and we're finished almost in time, and we're ready for official Q&A. And I also have my URL again there.
Just for entertainment, you were bringing up GUI libraries that don't rely on callbacks. Java 1.0 AWT, you would have a single function with a loop that would get the current event and then do inspection on the event to do some code. No callbacks involved. And thankfully, they got rid of that in 1.1.
Thanks, AJ, for making my point so well. I didn't remember. And that's when I used Java, back in 1.0 time, but then I got post-Java stress disorder. So,
Any answers?
well then, I'm all done. Thank you. Oh, one more.
So when you were talking about XML parsing with DOM, SAX, and then pull DOM, I think, which one is more scalable?
I'm sorry?
Which ones are and aren't scalable? You know,
Mini DOM, any form of real DOM is not scalable. It will take up all your memory and then shake you down and take the pennies out of your pocket to go buy more. SAX is the most scalable. Pull DOM, because basically it keeps calling you. It takes a linear time with you cannot take less than linear time with the width of the document, right? You have to look at all of it, even if it's boring. Pull DOM is an interesting compromise, which is almost as fast as SAX, but almost as handy. You don't actually have to build your own data structures, because when you reach a point close enough to the leaves of the tree, you tell it, okay, expand this node and all its children. Of course, if you do that and you're wrong in believing you're close to the leaf, whoops, you're in trouble. But for many kind of XML files, you kind of can do that, can afford to do that.
Thanks.
Well, then we are done. Thank you very much.